Within the span of exactly 1 month, two technological titans, Huawei and IBM, announced revolutionary chip architectures that will change your devices forever. They both realized the flat 2D era of microchips is dead, pivoting instead to 3D designs, where IBM stacks individual transistors like a skyscraper, and Huawei folds sprawling circuits into layers. And here is the crazy part. They arrived at these massive breakthroughs for completely different reasons, and by using fundamentally different physics. Welcome to Technoverse. Today, we're exploring the upcoming death of the 2D microchip. We're breaking down Huawei's new 1.4 nanometer equivalent architecture and IBM's mind-bending 0.7 nanometer nanostack to see exactly how they work and how they differ. Let's dive in. To understand these upcoming technologies, you first have to understand the massive obstacles each company is facing today. They both hit a wall, but they hit two completely different kinds of walls. First, Huawei's wall is geopolitics. Due to strict U.S. trade restrictions, China cannot import the advanced EUV lithography machines made by the Dutch company ASML. Because Huawei physically cannot manufacture traditional transistors smaller than 5 nanometers without this machine, they had to invent a clever workaround to stay competitive in the coming decade. IBM's wall, on the other hand, is physics. IBM doesn't face trade restrictions, but they do face the laws of the universe. After introducing the world's first 2 nanometer chip back in 2021, the industry realized something terrifying. Shrinking transistors horizontally on a flat 2D plane was causing severe quantum interference and overheating. They simply ran out of flat space. So how will Huawei solve their problem? In May 2026, at a major conference in Shanghai, they introduced a concept that aims to change the game. Since Huawei can't make physical transistors much smaller, they decided to change how electricity will travel between them. Huawei's semiconductor president explained that the biggest bottleneck to future performance isn't just the size of the transistor, it's the length of the microscopic wires connecting them all together. Instead of focusing on traditional geometric scaling, which is Moore's law, Huawei is using a new concept called the tau scaling law. Tau represents the time it takes for a signal to travel. Their goal isn't to compress physical space, their goal is to compress time. They plan to do this through a technique called logic folding. Huawei will take a traditional flat 2D circuit design and physically distribute it across multiple stacked layers. By stacking the circuits vertically, they replace long horizontal interconnect wires with ultra-short vertical ones.
The result? The signal travel time absolutely plummets. This boosts operating frequency and drastically reduces power consumption. You get the exact same performance jump as moving to a smaller physical chip without actually needing one. Huawei is debuting this in their Kirin smartphone chips in fall 2026. It claims an improvement in performance of 12.7% and a massive 41% reduction in power consumption compared to the previous Kirin chip using the exact same 7 nanometers node. Even crazier, just by folding the architecture, they achieved a 53.5% increase in transistor density, cramming a staggering 238 million transistors into every square millimeter. They're aiming to refine this technology to reach a massive 1.4 nanometer equivalent density by 2031.
Exactly 1 month later, in June 2026, IBM shocked the industry with a completely different approach to the future, the 0.7 nanometer 3D nanostack. Utilizing their advanced research labs in New York, IBM tackled the physics problem by reinventing the transistor itself. They moved the fundamental building blocks of processors into the third dimension. In a standard chip, the two types of transistors needed to process data, the N-type and the P-type, sit side by side. IBM's new 3D architecture stacks them directly on top of each other, using a design known as a CFET. Because the layers are built sequentially using ultra-thin wafer bonding, engineers can use completely different materials for the top and bottom layers to maximize their performance. This staggered 3D logic gate doubles the transistor density in the exact same footprint. We are talking about packing roughly 100 billion transistors into a chip the size of your fingernail. It offers up to 50% higher performance and 70% better power efficiency compared to their 2 nanometer chip. IBM expects commercial foundries to start mass producing these within the next 5 years, putting them right on track for 2031. So, what is the real difference between the two? While both will rely heavily on 3D vertical stacking to reduce signal delay, they are operating at vastly different scales. The goal: Huawei's primary goal is to circumvent the EUV equipment ban. IBM's goal is to overcome physical 2D scaling limits. The scale: Huawei is dividing macroscopic elements, literally folding entire logic circuits. IBM is dividing microscopic elements, stacking the individual N-type and P-type transistor channels. The node: Huawei is targeting an equivalent node, meaning it will act and perform like a 1.4 nanometer chip by 2031. IBM is targeting a physical node, creating actual geometric 0.7 nanometer structures for future production lines. Ultimately, both companies have proven one undeniable fact: the flat, 2D era of microchips is officially ending. Whether driven by geopolitical necessity or by the fundamental laws of physics, the path forward for the entire tech industry over the next decade is to build upward. If you enjoyed this breakdown, make sure to hit that like button, subscribe to Technoverse, and let us know in the comments, whose 3D approach do you think will dominate the future of computing? See you in the next one.